Welcome back, biology. Today I'm covering the next part of section 2.1, looking at the nature of matter. So yesterday we started talking about atoms and how atoms are made up of 3 subatomic particles. Then we transitioned to elements, and that elements are determined by the number of protons, and that the number of electrons determine its reactivity properties or its chemical properties, how reactive it is. Discussed a little bit about elements in living things, listed the 6, and I argued for 7, and then went into trace elements, and if you have deficiencies it can lead into some disorders, and then it kind of segued into isotopes and how isotopes have the same number of protons, but the number of neutrons is different, so you have a different mass number. And then finally wrapped it up with compounds. And what is a compound? Well, a compound is a molecule that has 2 different elements chemically bonded together, and I think I asked which one of these is not a compound, and hopefully you selected O3 because this is a molecule, not a compound. We only have oxygen present, even though I have 3 of them, but they're not different from each other, and nitrogen gas, N2, where the rest here are all compounds because they have 2 or more different elements chemically bonded together. So our discussion today is really going to be about bonds, okay? But before we do that, I guess I want to wrap up isotopes, just to clarify, because my picture wasn't 100% accurate. So isotopes, remember, they have the same number of protons because they're all carbon, and carbon is, the element you're looking at is determined by the number of protons. If I was looking at the number of protons of 7 and I look at my periodic table, I'd be like, oh, now I'm looking at nitrogen isotopes, right? So the number of protons and the number of electrons are the same. Okay, when you find an element in nature, you just assume that the number of protons and the number of electrons are the same. Where do neutrons play in? Well, isotopes are basically elements that have the same number of protons, but the neutrons are different. And as a result, they may have slightly different properties, but pretty much the same. So the only thing that's changing is really the number of neutrons. So the mass number here is denoted by this last number here, carbon 12. That means that I have 6 protons, and the mass number is 6. Mass number is protons plus neutrons. So 6 plus 6 equals 12. Mass number is 13. I have 6 protons. I know I have 6 because it's carbon. So if I could take 13 minus 6 and get to 7. Carbon 14. Well, it's carbon. The number of protons is 6. I can take 14 minus 6 and get 8 neutrons. So hopefully that clarified. I hope it did. Sorry if my brain's a little scattered. Woo. Okay, moving on to chemical bonds. So electrons surround the nucleus. They're not a part of the nucleus, they're outside the nucleus. And electrons are responsible for the chemical properties of elements because they are the ones involved in bonds. And so electrons that are in the atom's outer shell are called valence electrons. So here I have, let's just say that I'm dealing with an atom here, and it looks like maybe I have, we'll just say the white circles are the protons, okay? So I have 1, 2, 3. So I'd say, okay, I have 3 protons, okay? A little slow here, it's slow. And remember, anytime we find an element in nature, we're just going to assume that the number of protons and electrons match up. So how many electrons would I have? I would also have 3. Right. Now, when I figure out my valence electrons, these are the electrons that are in the outermost energy shell. So that means I kind of need to draw them in. So here are the rules. There are no rules. I'm just kidding. Yes, there are rules. The first energy shell can only hold 2 electrons. Okay, so you go 1, 2. But how many electrons do I have? I have 3. So that means I got to go to the next outer energy level and fill it in until I get to 3. So I'm already at 2, and now I'm at 3. Now, the second energy level can hold 8. So I drew it. I have 3 protons, I have 3 electrons, and the question is, how many valence electrons do you have? You look at the outermost energy shell. Now look, there's only 1. I have 1 valence electron. This element is going to be highly reactive because it needs 8 to be fulfilled. I need to fill this outer energy shell. That's what atoms want to achieve. They want to be full, okay? So this atom or element is going to be highly reactive because it's going to do everything it can to get rid of that 1. So that way this shell disappears and you are left with a full outer energy shell, in this case 2. Now the cool thing about our periodic table is that it's set up in a way that there are several different patterns. The columns are all elements that behave the same, okay? The rows increase by atomic number as you go from left to right. So elements in group 1 all have 1 valence electron, and elements in group 2 all have 2 valence electrons. And when you skip the transition metals, they just mess everything up. But if you continue on to over here with group 13 and just say, well, I went 1, 2, this is going to be 3. These guys all have 3 valence electrons. And carbon has 4 valence electrons. And nitrogen, group 15, all of these have 5 valence electrons. And 6 valence electrons. And 7 valence electrons. Until finally you get to group 18 where the outer energy level is completely filled. And we call them the noble gases because they are inert and unreactive and don't bond to anything. So to prove to you that everything in group 1, maybe I just drew lithium, really. Here's lithium. 3 protons, 3 electrons, 1 valence electron. Now let's just quickly look at sodium. Sodium, wow, everything's so slow. Sodium, how many protons it has? It has 11. So if I need to draw in these electrons, I got 1, 2, then I go 3, 4, 5, 6, 7, 8, 9, 10. So I have 8 in this ring because that's how many the second ring can hold, but I have 10 overall and I just need 1 more. So I actually have to draw in a really bad circle, holy crumbs, and draw 1. So look, it's got 1 valence electron, just like we had with lithium. So all of these elements in group 1 have 1 valence electron. So there are patterns here. So there are 1 of 2 ways for atoms to achieve this outer full shell of electrons. They can either give 1 up or transfer, and we call those ionic bonds. So when 1 or more electrons are transferred from one atom to the other, call it an ionic bond. Atoms are electrically neutral when they have equal number of electrons and protons, but sometimes we do encounter an atom where the number of electrons and protons are unequal. And if they're unequal, now you have a charge. So an ion, by definition, is an atom that has a charge. It can be a positive charge or a negative charge. Sometimes it can be +1, +2, +3, +4, +5. Sometimes it can be -1, -2, -3, negative. I've never actually seen a -4, but so on and so forth. So if it has a positive charge, we call it a cation, which means there are more protons than electrons. So kind of think of it as a seesaw where the number of protons and electrons are the same, but all of a sudden now I get more of 1. So let's just say I get more of 1 here, more protons. Okay, so I'm going to be more positive. So more protons means you're going to be more positive. Whereas the opposite, anions, you're going to have a negative charge because you have more electrons than protons. And so one way to help you remember the difference between a cation and an anion is that a cation, cats have paws, positive, right? And an anion sounds like onions, and onions make you cry. So great way to help you remember the difference between a cation and an anion. So here we have a transfer of electrons going on between sodium and chlorine. Sodium had 1 valence electron here, and you can see that's being transferred. Chlorine has 7. And if I go back to this previous table, here's chlorine, group 17. Okay, 1, 2, 3, 4, 5, 6, 7 valence electrons. So it really just needs 1 more to have a full outer energy shell. It's so much easier to get that 1 electron than it is to give up 7. So it's also going to be highly reactive. So these two are perfect for each other. Sodium's like, I want to get rid of one. And chlorine's like, I really need one. Oh my gosh, it's a match made in heaven. So sodium gives up this valence electron to chlorine, and now we have formed ions that are held together by attractive forces because sodium now has a +1 charge because it lost an electron, and chlorine now has a -1 charge, and we have opposite charges and opposites attract. So ions are atoms that have charges. How does that play into ionic bonds? Well, ionic bonds are held together by these oppositely charged ions. So here again, another diagram showing sodium's 1 valence electron being transferred over to chlorine, so chlorine gains it, and now we have a positive charge for sodium and negative charge for chlorine. They are attracted to each other, and this is actually how ionic bonds are solids and have crystalline structure, and they arrange themselves as cool little lattice structure. It's all because of these attractive forces. So I guess I can go through lithium chloride. So lithium is in group 1 as well. It has 3 protons and 3 electrons. So if I were to do the valence electrons for lithium, the first energy level can hold 2, and the second one can hold 8, but I only need to get to 3. Whereas chlorine over here has 17 protons, and so we assume that it also has 17 electrons. Now I got some work to do. The first energy level can hold 2. The second energy level can hold 8. I'm racing against the clock here. I can do this. All right, I am at 10. I should have completed this slide. So sorry to be wasting your time. So I'm at 16, and here's 17. And so you can see that I have an open spot here, and lithium doesn't want this electron, so it literally makes the transfer, and we're just going to see if I can slide all of this over, and we have forces of attraction holding this bond together. So ionic bonds. Named bond, ionic bond. Taken, not shared. Now that's one way electrons can fulfill an outer energy level. The second way is through covalent bonds, where atoms actually share electrons. So sometimes you get halfway between 8, right? Like if I'm at the low end of 1 through 8, it's like 1, 2, 3. It's easy for me to get rid of those electrons. But if I'm at the high end, I can get those electrons. But if you're in the middle, it's actually easier to share than it is to get rid of those 4. So when they share, if you share a single pair, then it's called a single bond. If you share 2 pairs, it's called a double bond. If you share 3 pairs, it's called a triple bond. And a structure that results from these covalent bonds is called a molecule. So it takes way too much energy to steal 4 electrons, so instead it's going to share them, and carbon is smack dab in the middle of between 1 and 8. So carbon tends to share a lot of electrons. Another molecule, like water, also shares. So here's oxygen. Oxygen on the periodic table is number 8. So 1, 2, 3, 4, 5, 6, 7, 8. It needs 2 more electrons. So 1, 2, and hydrogen has 1 valence electron because it's in group 1, so it really just needs 1 to fulfill its first energy level that can hold 2 electrons. So these 2 are perfect for each other, so they will share. As you can see here, they're going to share these electrons. Okay, I don't know if I have time to go off on a little tangent here, so maybe in class I'll go off on a tangent. That does it for chemical bonds. Basically, I just recapped yesterday's lesson and then threw in on top the difference between ionic bonds, where you take or transfer electrons, and then covalent bonds, where you share electrons, because it takes way too much energy to either gain 4 electrons or to lose those 4 electrons because you're in the middle.